Have you ever wondered how the vast universe of numbers organizes itself? Welcome to a journey through the hierarchy of numbers, a fascinating structure that uncovers the relationships and unique characteristics of different types of numbers. Let's start with prime numbers. These are the integers greater than 1 that have no positive divisors other than 1 and themselves. You can identify them through prime factorization, dividing the number by smaller primes to see if it's prime. What's so special about them? Well, prime numbers are the building blocks in number theory, cryptography, and various mathematical algorithms. Next up are the everyone numbers. These represent all whole numbers up to a certain prime number, including the prime number itself. You can derive them by counting all integers from 0 up to the prime number. They encompass both even and odd numbers, helping you understand the distribution and properties of whole numbers within a given range. Speaking of even and odd numbers, these are the integers divisible by 2 and those that are not, respectively. You can identify them simply by checking divisibility by 2. They play vital roles in arithmetic, grouping, and mathematical modeling. In this segment, we will delve into the logical transition from even to odd numbers. This phenomenon is not only fascinating, but also forms the very fabric of the number system. Starting with an even number, which is any integer divisible by 2, subtracting 1 will yield an odd number. This transition is akin to disrupting a balanced pair, resulting in an unpaired unit, thus forming an odd number. The implications of this transition are far-reaching. It enhances arithmetic intuition, aids in mental calculations, and boosts problem-solving capabilities. In an educational setting, emphasizing this transition can facilitate the comprehension of basic mathematical concepts, particularly for students learning arithmetic operations. Moreover, this transition can be geometrically visualized. Imagine a line with points representing even numbers. The spaces between these points represent odd numbers, signifying a shift in balance and symmetry. Finally, real-world analogies can further illustrate this logical transition. Consider pairing and unpairing objects. Removing one item from a pair leaves an unpaired item, much like transitioning from even to odd. By understanding this transition, we can develop a deeper appreciation for the structure and logic inherent in the number system. So let's dive into exploring this intriguing transition further. As we transition from even to odd numbers, we find ourselves entering the world of prime numbers. Prime numbers are a unique set of numbers that have only 2 distinct positive divisors, 1 and the number itself. By definition, all prime numbers are odd, with the notable exception of the number 2, which is the only even prime number. This is because any other even number can be divided by 2, thus having more than 2 distinct divisors. The connection between odd and prime numbers is truly fascinating. While not all odd numbers are prime, all prime numbers except for 2 are odd. This is due to the inherent property of odd numbers, which allows them to have no other divisor besides 1 and themselves, making them prime. Consider the number 3. It's odd, and it can only be divided by 1 and 3 without leaving a remainder, making it a prime number. On the other hand, the number 9, although odd, isn't prime because it can be divided by 1, 3, and 9. Understanding this progression from even to odd to prime numbers provides a deeper comprehension of the world of mathematics. It's like a journey, beginning from the symmetry of even numbers, moving towards the disruption of balance with odd numbers, and finally reaching the exclusivity of prime numbers. So as we step into the world of rational numbers, remember this journey. It's a testament to the beauty and diversity inherent in the world of numbers. Let's continue exploring. Rational numbers, on the other hand, are numbers expressible as fractions of integers. Any number that can be represented in the form of a fraction where the numerator and denominator are integers, with the denominator not equal to 0, is considered rational. These numbers are foundational in mathematics and are extensively used in calculations, measurements, and comparisons. Then there are irrational numbers. These are numbers that cannot be expressed as fractions of integers. You identify them by showing that they cannot be written as the quotient of 2 integers. Why are they important? Irrational numbers represent quantities such as pi, the square root of 2, and e, filling the gaps between rational numbers on the number line. Natural numbers are positive integers starting from 1, the basic counting numbers used to enumerate objects or quantities. These are fundamental in mathematics, providing a basis for arithmetic operations, sets, and number patterns. And let's not forget about other types of numbers. These include additional subsets beyond those explicitly mentioned, such as complex numbers, hyperreal numbers, surreal numbers, and others. These number systems are derived and defined using various mathematical concepts and methods, and they expand our understanding of numbers beyond the conventional boundaries. In summary, the hierarchy of numbers is a complex yet fascinating framework that helps us understand the diverse properties and applications of numbers, from prime numbers to everyone numbers, even and odd numbers to rational and irrational numbers. Each subset of numbers holds its unique significance in the vast landscape of mathematics. So the next time you see a number, remember, it's not just a number, it's a part of a grand hierarchy that forms the foundation of mathematics. Now that we've explored the different types of numbers, let's delve deeper into the underpinnings of number theory. This branch of mathematics is concerned with the properties and relationships of numbers, particularly the integers. From the basic concepts of prime numbers, everyone numbers, even and odd numbers, to the more complex rational and irrational numbers, and even the natural numbers, each type of number plays a key role in the development of number theory. Let's start with the what. Number theory is a branch of pure mathematics devoted primarily to the study of the integers or whole numbers. It deals with the properties of numbers and the way they relate to each other. Next, we have the how. Number theory uses tools from a wide variety of mathematical disciplines, including, among others, algebra, analysis, and topology. Then we discuss the why. Understanding number theory is fundamental to many areas of mathematics, and it has applications in cryptography, computer science, and more. Finally, the when. Number theory has been studied for thousands of years, and it continues to be a vibrant area of mathematical research. So whether you're a math enthusiast or just curious, we hope this deeper dive into the world of numbers has given you a new perspective on the numbers all around us. Remember, every number has a story to tell and a role to play in the grand scheme of mathematics. As we move forward on our numerical journey, let's now focus on visualizing these different types of numbers using the concept of sets in mathematics. A set is simply a collection of distinct objects, considered as an object in its own right. First, we have our prime numbers set denoted by P. This set consists of numbers greater than 1 that have exactly two distinct positive divisors, one and themselves. In set notation, we write it as P equals sign 2, 3, 5, 7, 11 L dot. Next, we have the everyone numbers set denoted as W. This set comprises all the whole numbers up to a given prime number, P, including P itself. We denote it as W equals sign 0, 1, 2, 3 L dots P. Moving on, we have the even numbers set denoted by E. This set consists of integers that are divisible by 2, denoted as E equals sign 2, 4, 6, 8 L dots. Lastly, we have the odd numbers set, denoted by O. This set comprises integers that are not divisible by 2. We denote it as O equals sign 1, 3, 5, 7 L dots. Now let's illustrate their relationships using set diagrams. Imagine a large circle representing the prime numbers set. Inside it, we have a smaller circle representing the everyone numbers set. This smaller circle is divided into two separate sections, one for even numbers and one for odd numbers. To summarize, the everyone number set encompasses all the numbers from 0 to the prime number, P inclusive. The even numbers set and the odd numbers set are disjoint subsets of the everyone numbers set. Prime numbers are a subset of everyone numbers. Every prime number is included in the set of odd numbers, but not every odd number is a prime number. This set diagram effectively illustrates the relationships between prime numbers, everyone numbers, even numbers, and odd numbers using set theory notation. As we delve deeper into our exploration, we now turn to the foundations of number theory. This is a branch of mathematics dedicated to the study of the integers and, more broadly, number sets like the ones we've just discussed. The what, how, why, and when of number theory is a fascinating journey, so let's embark on it together. Firstly, what is number theory? It's simply the study of numbers and their properties. It's about understanding patterns, relationships, and structures within various number sets. It's about looking at numbers not just as quantities, but as interconnected entities with unique properties. Next, how do we study number theory? We use various mathematical tools such as set theory, which we've just illustrated, and algebraic structures to understand these properties and relationships. We also employ logic and proof techniques to establish truths and solve problems. The why question is always intriguing. Why study number theory? The beauty of this field lies in its simplicity and its complexity. Prime numbers, even and odd numbers, rational and irrational numbers, natural numbers. These are simple concepts, yet their properties and relationships can be mind-bogglingly complex. They're like a puzzle waiting to be solved, and the solutions often have profound implications, not just in mathematics, but in areas like cryptography and computer science. Finally, when did number theory come into existence? The origins of number theory can be traced back to ancient civilizations, where the properties of numbers were studied out of intellectual curiosity. But it was in the 17th century, with the work of mathematicians like Fermat, that number theory started to take the shape we recognize today. So, as we continue our journey, remember that every number you encounter, from the simplest to the most complex, is part of this grand tapestry of number theory. Each one has a story to tell, a secret to reveal. And that, dear viewers, is the true beauty of numbers. Stay tuned as we unravel more numerical mysteries in our upcoming segments.